Hi class. So I want to investigate the idea of concavity a little bit further in this video, and I want you to look at the function that you see here. And we talked about the general scenario of when y double prime is equal to 0. That would appear to indicate most of the time that something's going on that we need to investigate. And I say most of the time because there'll be another scenario that I'll bring up in a later video. But when you see a situation where y double prime is equal to 0, immediately you should be aware that something important may be happening. And it indicates that in your graph or in your function, potentially we have what's called a point of inflection. Point of inflection I've defined here. In differential calculus, this is defined as a point on a function where it changes concavity. It coincides with the steepest point on a curve between two extrema. If you look at my diagram that I've drawn here, take a moment and pick out where you think the point of concavity is. Just look at that and decide. Okay, if you want to pause the video, you can. If I was just eyeballing it, I would say that the point of inflection, and if I said point of concavity, I apologize, but I would say that the point of inflection is right about here. Somewhere like right, it may coincide exactly with the x-intercept actually, but that's not always going to be the case, okay? So don't mix the two up. At that particular point on the function, we have what's called a point of inflection because it's a transition point where the graph goes from being concave down to suddenly inverting to concave up. Now the transition point is known as the point of inflection, and the point of inflection is the steepest point that the curve reaches on its downward slope as you go from left to right, and then anywhere after that point, the slope begins to shallow out and move into this basin or this valley here, okay? So you can see that it's defined, therefore, as a place of transition in a function where the function shifts from being a concave down function, reaches its steepest it'll ever get, and then begins to move into a concave up pattern. Okay, and this point of inflection must occur between two extrema because any other place on the function that you observe here, there's no extrema now to the right. So if you go here, it just keeps getting steeper. So it's not going to transition again. It's in a concave up kind of loophole where it just keeps going. And in this part of the graph over here, it just keeps going more and more concave down. It gets steeper and steeper, okay? So we have what's called a point of inflection. And it's a very important idea because it helps us to picture what the graph of the function might look like. And the point of inflection in a function can be observed at the place where the second derivative is equal to 0. But you have to be very careful about this test. We call it a test. What we'll see is that sometimes you can be fooled by this. The important thing to understand is this, is if I were to take anywhere to the left of this point of inflection, all right, I would find that the second derivative produced negative results because my function is concave down. However, if I was to take a test point anywhere to the right of my point of inflection, I would find that my second derivative produced positive results. And that would be because my function is concave up anywhere to the right. So there's actually two really important things then that would define a point of inflection if we were trying to identify it algebraically. Those two important things would be, first of all, that the second derivative is equal to 0, but secondly, that the sign of the second derivative changes from either positive to negative or from negative to positive on either side of the key point of inflection. And the reason I bring this up is because what I was going to say in a later video, but I might as well just bring it up now, is consider the case of a function such as this, which is a kind of roughly drawn version, of y equals x to the fourth. Okay, so sorry about that. Consider this case of y equals x to the fourth, right? Now, if I look at y equals x to the fourth, it's pretty clear that this is a quartic function that is continuously concave up over its entire domain, all right? And that can be just observed by the bowl-shaped structure of the function. If I were to take the first derivative of this quartic function, what I would find is that I would get 4x cubed as my first derivative. And then I would, if I set that equal to 0, I would find that 0 occurs right at the origin, right? In other words, when x is 0, the derivative is 0, which makes sense. The bottom of the function, or the absolute minimum, is at 0, 0. If I was to take the second derivative of my function, I would find that that is 12x squared, okay? Now, here's the interesting thing. If I was to plug in 0 to my second derivative, I would find that at x equals 0, the second derivative also is equal to 0. And then, if I didn't know any better, I would conclude that this point, which is the minimum, is also a point of inflection. But that's not true, because at this point at the minimum, the function is not shifting from being concave up to concave down, or vice versa, concave down to concave up. This function is always concave up. So that is an important consideration. And that's why I made a second point earlier when I said, in order for something to be a point of inflection, the function must transition from being concave up to concave down over the point of inflection, or from concave down to concave up. And if you take a look at this function here, you can see it's always concave up. If I was to take a sample point to the left of the point 0, 0, and plug it into my second derivative. So for example, if I was to take x equals -1 and plug it into my second derivative, I would get a result of positive 12. So I would get a positive second derivative indicating upwards concavity. And if I was to take x equals +1 and plug it into my second derivative, what I would find is that I would also get a value of positive 12, also indicating positive concavity. So what you see is, on either side of my place where the second derivative is equal to 0, the result is positive concavity, and that means that I have a scenario where, yes, the second derivative is equal to 0, but it is not a point of inflection. Point of inflection must occur when the concavity changes over that point. So just keep that in mind, and that will be something that definitely comes up, and we'll identify a point of inflection when we get into more complex functions, such as cubic functions like this one here, okay?